All right, we're going to talk about normal deviation. Hopefully you already know how to put a list in your calculator and come up with the mean or average, as well as the standard deviation, which typically we use the sample standard, or in some cases we might use the population standard deviation. And the basic idea is this is what our middle number is. So maybe our middle number is 30. And for the example I'm going to be talking about, we're going to have fish that on average are 30 centimeters in size, so the mean is 30. And their standard deviation is 4. Okay? And what standard deviation is, once again, it's how much variation there is from the center. It's a measure of if there's a lot of variation, this number might be big or small relative to the sample size or compared to other data sets. And in a normal distribution, as I get further away from this mean, I get fewer and fewer values. So if I was going to do a histogram, my bars would get smaller and smaller, but we typically represent it as a curve. And we do it what's called a bell curve or a normal curve, and it looks something like this. And I'll show you a better example of one in just a moment. But basically that means from here out 1 standard deviation, or out 4 this way, so 34, or back 4 this way, or 26. Between those 2 points, if this is truly a normal deviation, this is actually 68% of our data. We can be expected that if we go out and take sample data, that 68% of our data will come back between those 2 values. And if we go out another standard deviation, we're expecting that actually 95% of our data will be between those 2 values, which in this case, if our standard deviation is 4, is 38 and 22. Is that right? And if I go one more further, there's very little out here. But if I go all the way out, there's 99.7. And this is usually called the 68, 95, 99.7 rule. And it's just how far I get away from that center, how much data am I expecting to show up in a sample or in a population. So that's the basic idea. Now, the kind of questions I might ask related to this is like, well, let's say we had a population of 500 fish, which you can't see. Those are my fish. 500 fish. If we started pulling these at random, I mean, like, how many would we expect to be, what percentage would we expect to be a certain size, what percentage would be above or below a certain size, how many would be above or below a certain size. So I can ask some practical questions here. So the first question I could ask is, what percent is smaller than 26%? So what percent is smaller than 26%? Than 26 centimeters? Actually, I'm looking for smaller. And just from looking up here, I was like, well, that's all this down here. So if I knew what this was, I could be reasonably sure. And I could kind of figure this out from here, but I've got a better graph that'll show that, which is this one right here. And once again, so we've got fish that are 30, and the standard deviation is 4, so 26 and 34. And if I go out another 4, it's 38. If I go down another 4, it's 22. And so I am looking for, once again, how many are below 26. So I'm like, oh, well, 26 is 1 standard deviation away. And then this is broken down in those percentages. 9.2 are between that amount and another 4.4 and a 1.7 and a 0.5 and a 0.1. And if I add all those up, all this stuff over here is 15.9 if I've done my math correctly ahead of time. So 15.9% of the fish that I pull out of this population of 500, I'm expecting to be below 26. And that won't happen every time I pull fish out, but in general, that's what should happen. Now, another question I might ask is, so this is a different question. That was a percentage. I'm asking how many are bigger than 36 centimeters? Well, 36, I'm like, oh, well, this is here, and this is nicely broken up, so 36 is going to be right here, and then I can just say, well, bigger than this are those percentages, so I can add those together, and that comes out to 6.7%, and that's not answered the question. What I have to do is actually say, well, how many? So our total population was 500, so to find that, I got to say, well, 500 times 0.067, because I need to convert that to a decimal. And then I multiply that out, and I believe that's 33.5 because I've done this problem a couple times today. So about 33.5, and that makes sense because 10% would be 50, so 33.5. So about 33 to 34 fish I would expect up here out of my population of 500 if this is a normal distribution. Okay, and another question that I might actually ask how many are between 26 and 38. And so in that case, I would do kind of a similar kind of thing. I'd say, well, 26 is 1 standard deviation away, and 36 is 1.5 standard deviations up. And I'd count all those up, and I'd add all those up, and I'd find the percent, and then I'd multiply my percent times 500. So that's a typical kind of question is I can find it above or below some amount, or I can find it between 2 points. And once again, this is just kind of adding up, well, what are the percentages in between those 2 points? Now, the more complicated question is when I ask, what percent are smaller than 25 centimeters? Okay. So I'm like, oh, that's not so hard. 25's over here. Oh, we'll see. This is 26, and this is 24. So 25 is right here. Now, this is still easy enough to eyeball. And I'm like, well, it's 1.25. I could kind of estimate what that is. It's less than 15.9, but more than 6.7, which is the endpoint. So I could kind of estimate it. But we really need a better way of doing this. We need 2 better ways. First of all, this landed exactly at 1.25, but what if I ask you like 25.1 or 25.3? I need a way to figure out, well, what exactly, how many standard deviations down is that? I can tell it's 1.25 down. But I need a better way to do it. So there's kind of 2 tricks here. First of all, to calculate how many standard deviations away there's 2 questions you need to ask yourself. The first of which is, how far am I away from the mean? So to do that, I'm like, okay, well, my mean is 30. My value that I'm asking about is 25, so my distance from the mean is 5. Okay? And actually, I'm doing this backwards, though. We typically do the other one first. We do the number that we're talking about minus the mean. And the reason we do that because we want to know that we went in the negative direction. Okay? So that's my distance from the mean, 5 down. But that's 5 total. That's not the number of standard deviations, and that's actually very important. So I'm going to say, oh, well, to do that, I can just take the standard deviation, which in this case is 4, and just divide. Because there's one full one, that would be the 4, and then there's another quarter left over. And so you can reason that out, but this is important. If you've got numbers that are irregular, you can just always say, well, what's my distance? And then what's my standard deviation? Because this will break my distance into how many standard deviations. And usually this is written as x minus mean over either s of x or sigma. All right, so that's negative 1.5. That is an easy way to get the number of standard deviations away from the mean, which we kind of already knew. We're like, oh, well, it's 1.25, I can tell from there. Now, how do I find that number? I mean, this is a nice, neat chart if I'm only doing things at ones and halves. Well, on the other side of it, I have what's called a z-table. This is probably a little hard for you to read on the screen. These come in different flavors, but this one basically says, hey, what is the percentage for some z number for some number of standard deviations above the mean? So you'll notice it starts at 0.5 because at 0, there's 50% below this line. And if I go up 1 standard deviation, it's actually 84.13%. If I actually flip it over, I can see that, oh yeah, 84.1, this is cumulative. That's where 1 is. So that matches up. So what I'm looking for is 1.25. So I'm going down to 1.2, I go over to 0.5, and there's 0.84894. So 0.8944 or 89.44% is below this line. Unfortunately, the problem is my number was over here. My 25 was down here. Well, this is where I have to get clever and actually kind of read this here. I need to flip-flop. What I really want, I don't want this whole thing. I actually want this area over here, but I want it down here. So what we do is we subtract. We're like, oh, well, this right here, that's that space. So 1 minus that will give me this. So 1 minus 0.8944. That's going to give me 10.6%. are out from 25 on down. This logically kind of makes sense because we knew for 26 it was 15, so that needed to be a little bit smaller. And so the Z table, all it does for you is it breaks down things at a smaller value than halves, because this is easy enough if you're going by ones and halves, how many standard deviations out. But if you've got something that's an irregular amount, this is the best way to do it. There are ways to do this in your calculator, which I invite you to look at. Look it up on the internet. How do I do a Z-score on my calculator? But tables are best to start with because it's a little more straightforward what's going on. And I think that is enough. Thanks.